Hi, everybody. I'm Mike Deutsch, and I'm here to present this pre-recorded session for OAME 2020 that I'm calling Math by Way of Microbits. Welcome to the session. You're watching this pre-recorded, coming to you live from my basement in Montreal, and I want to start by thanking the organizers of OAME, first for inviting speakers, second for accepting this talk, and third, for helping the show go on. I came to my first OAME in 2019, last year, in Ottawa, and just had a blast. So I'm really excited to present again. So this is a reprise of last year's session, Math by Way of Microbits. And as the session description suggests, I've updated it to put more focus on sense making, the pedagogical approach that a lot of OAME talks speak about, that I've taken to heart and have started to build into KCJ Jeunesse programming. So with that introduction, let's begin. Math by way of microbits. I'll actually start by talking a little bit about KCJ Jeunesse, the organization I work for. So KCJ is a nonprofit, a charity that began in Montreal and is now present all across Canada. We have people in every province. And as an organization, we're bilingual. We deliver all of our services in English and French. And what we produce is materials and workshops and teacher training, dealing with computational thinking, coding, and artificial intelligence. So I'm going to share with you today a portion of that. We do Scratch, we do microbits, we do AI, and we do other platforms besides as they come and go over the years. We're also the sponsors of Code Club all across Canada. So you may have seen a Code Club, or you may have seen someone from KCJ Jeunesse come into your classroom, or you may have even attended a teacher training seminar. In 2018-2019 school year, we were everywhere in Ontario, as you see on the map here, working with all kinds of school boards. And in 2019-2020, of course, we've been cut short for the time being, but we've had 4 in-person teacher training events, 2 in English, 2 in French, and almost 300 in-classroom workshops across the province. So we're no strangers to Ontario, and we love working with you all. So I'm based in Montreal, but we have a great team around Ontario. Our primary audience at KCJ is middle grade schooling, grades 3 to 8. We focus primarily on generalist teachers and students. So by that we mean we're not so focused on specialists. We don't get deep into STEM and robotics. What we are really good at is being the first step or two on your journey into coding in a way that you could use coding for all different kinds of curricular and non-curricular applications. As far as our pedagogical approach, computing education varies. There are lots of different approaches to it. You may have seen, if you've done coding lessons in the past, a kind of follow me approach, where I build something and I do all of it and then just tell you to follow me and copy what I did. We try very hard not to do that. We try to teach in a way that supports sense making, a topic close to OAME's heart. And our feeling is that when you teach the right way, you give teachers and students agency, they're able to develop self-efficacy. And of course, there's positive affect that comes out of that. So myself, I'm the director of educational R&D at KCJ. I came to KCJ and computing education as a second career. I spent almost 20 years in the software world and doing various jobs as a product manager. I joined KCJ 2 years ago in 2018. And I've also, for a few years now, been working on an MA, a master's degree in math education at McGill. And so a lot of the pedagogical approach that KCJ has been adopting in the last couple of years comes from the things that I'm learning in the math community. You all are doing fantastic, innovative stuff. And if you're an OME veteran, you know that. So here's what I expect your profile looks something like. You're an experienced teacher if you're attending OAME, probably. You already know mathematics, you know the content that you teach, and you know how you like to teach it. Um, you may have been attracted to this session because you're aware of microbits and you have microbits uh, accessible to you, or maybe you're just curious about investing in them. And you want to try building an exercise that explores math through code. So I don't assume that you've done any coding. Um, you won't need any previous experience to complete the things that we're going to do here. So I say maybe you've done some block coding before, Scratch or Blockly or something like that, but maybe you haven't, and that won't hurt you here. Okay. So here's a rundown of what I expect to cover here. I'm going to start by laying some context. I'll talk about the background of math and coding and how they fit together. I'll connect that back to some of the things that I saw at OAME 2019 and the pedagogical approach that KCJ tries to use. And then we'll actually look at a microbit and how they work. And from there, we'll spend the bulk of our time demonstrating 5 starter projects and tasks, classroom tasks that go along with it, that are focused on number sense and numeration and patterning and algebra. Those are the mathematics strands in the Ontario curriculum that are most closely aligned with what you'll see here today. So I expect, because this is pre-recorded, you'll be able to build along with me. Much like we do when we teach online remotely, like in classroom webinars, I'll build some things on the screen. Just by necessity, I don't have the ability to turn it over to you and ask you, well, how do you think you'd do this, or let you tinker. So what I'm going to do is demonstrate how these things are built. And then I'll leave the code on the screen where you can pause and then build along to match me. And then I hope that you'll be able to brainstorm some adaptations for how you would use this in your classroom. What I think you'll find is that the code over the course of these 5 projects, the code over these 5 projects will slowly build in complexity. We won't ever reach anything that's too intricate for you to understand, even if you're a newcomer. And as we build up the code complexity across those 5 projects, you'll see that the tasks you can accomplish with those, the instructional routines you can do, also get a little more complex and a little more rich mathematically. And my hope is that the two will reinforce each other. I'm going to show you a manipulative, essentially, built on a microbit. We'll talk about what you can do with an instructional routine that uses this manipulative. Then we'll have to understand, okay, well, if I want to build that, what are the code steps that I need to build in order to get the microbit to do this thing? I'll have to understand a little bit of code to build it. Then I'll do that instructional routine, and that probably will prompt me to think, well, okay, this is cool. What if I wanted to push this further? I'll have to think about mathematically, how do I want to go further, and then translate that into code, and back and forth and back and forth, and you'll see that expand over 5 projects. Okay, so a little bit of mathematical pedagogical background. There's actually quite a long history, several decades, of computing education overlapping with math. There are some very natural surface level reasons, which are that there's common terminology and common mechanisms between math and computing. Things like repeating the same step multiple times, holding on to distinct values at the same time. But there's actually commonalities deeper than that, and those include the reason that coding activates so many of the practices that we try to develop in math. The mindset that you take on as a coder is very similar to the mindset you take on as a mathematician, performing calculations, trying to prove and explore and make models work. So I've taken a quote here from Mark Guzdial, who's a computing education researcher and professor. And he actually comes from the original school of computing education, which was Seymour Papert and the Logo School. Mark is now a researcher at the University of Michigan, and he presented this at the Special Interest Group for Computer Science Education, SIGC, which is part of the ACM, the Association for Computing Machinery. And what he said was that teaching mathematics with code is a unique learning experience. In this kind of class, students have opportunities to quote unquote teach mathematics. Not just learn mathematics, but teach mathematics. So what does he mean by that? When a student writes code, the student is teaching the computer how to complete a task. And that's a very deep idea that comes from the very first generation of computing education with Logo and the turtle out of MIT. You may have heard the name Seymour Papert. Uh, he and others were the ones who became the originators of that. So I can even link that to specific mathematical processes that are in the Ontario mathematics curriculum. This is the grade 1 to 8 math curriculum, and the URL is there. So when you're coding, just as in math, you're problem solving. You have to reason and prove out why your ideas will work or not work. You reflect on the things that you tried and succeeded or failed at. You have to choose which tools from among the ones that are at your disposal, et cetera, et cetera. So there's some real big commonalities. Next, I want to talk about OAME from last year. That was my first time at the conference, and my eyes were really opened. So I've been studying this academically for a few years in my master's program, but to see an entire conference full of speakers and attendees nodding their heads and really getting these ideas was just spectacular for me. So Ontario math community, you're doing something right. I'll talk specifically about two speakers that I remember very clearly and I took photos from. One was Fletcher. Last year, he challenged us to think about two different things that I thought were worth discussing here. One is, are we asking students to learn math in order to solve problems? In other words, okay, kids, I'm going to show you how this part of math works. I'll just instruct you on how to do this. Then we're going to pivot to solve problems where these tools are helpful. That I think is what he takes to be the classic way of teaching math. But now there seems to be a pendulum swing, right? And we've reversed that. So the popular way of teaching math more and more is to confront kids with problems that they're going to have to grapple with without already knowing the mathematical tools that will get that job done. And the way he positioned that is to flip it around, that we're asking them to solve problems in order to learn math. The problem comes first, and that's how we confront problems in the world. We have to figure out, or maybe invent, the tools to solve those. Second idea I captured from Graham was he challenged us to think, in any given hour of math instruction that we do, who is in control of the learning, the teacher or the students? And he has this bar chart here. The classic math room probably looks like the teacher's in control of the learning, doing more and more instructing. The students are absorbing and then trying to repeat back or do what the teacher has modeled. And he challenged us to invert that. The second person that really struck me that I captured was Marian Small. And she and a number of other speakers illustrated a bunch of tasks that were very, very thought-provoking. And she said in particular, here are some tasks that ask students to think. She had a very specific definition of that. To think, the way she was thinking of it here is to make sense of something and figure out what to do. So contrast a more classic way of asking this kind of task. Students, I want you to decompose the number 42 into tens and ones. That might be the old way of doing it. And the new way might be, what are the ways that we could decompose 42 into groups? And why? So it's easy to see how the second one pulls the student's attention to very different things than the first one does. In the first one, it's presupposing that I've taught you how to decompose into tens and ones, what tens are, what ones are. The second one doesn't seem to presuppose that. You could give that problem to a younger student who doesn't know the rudiments, and you just see what sense they make of this. And in a classroom full of kids, you'll find interesting things. And from that, you can consolidate their understanding and start to give things formal names. So I sat at OAME 2019 and just really loved this. It brought so many things together that for me are directly applicable to teaching coding. And so that's why, in the spirit of those things I just discussed, in the rest of this workshop, we're going to build 5 sample projects, 5 simple projects together. As I said, they slowly build up in complexity. And the idea is that you and your students will be able to build these yourselves and use them in the classroom like manipulatives that you yourself have built in instructional routines. So you probably already have instructional routines that you lean on a regular basis. And my hope is that these will fit right into that. And I want to be clear, in contrast with other kinds of coding education you may have seen, other coding lessons, the emphasis here will not be on, what amazing things I got this microbit to do. There's plenty of room for that later on. But when you're a beginning coder, it's better to put the focus on the thinking that I can do with this programmed tool that I made. And that's where we're going to look today. The coding that goes into the microbit and the mathematical thinking that you do with the microbit will reinforce one another. Okay. So as I say, I've been inspired by OAME and this school of pedagogy. And so I've built an instructional routine that we now use pretty often at Kids Coach NS. When we walk into a classroom and introduce students to microbits, we don't simply open up a browser and start to code. What we've started to do is start with a finished product. Start with a microbit or a Scratch project or whatever platform we're teaching that day. Start with a finished product that we've built that has our thinking embedded inside this and our tinkering and our mistakes and corrections built inside here. And we invite students into an instructional routine. And we ask them, much like you would in math class, to notice what you see on this microbit, notice what it's doing, notice how I'm interacting with it, and think about what can't you see that you'd like to know more about. So just like a classic notice and wonder routine that you've done in math, this puts everybody in the classroom on an equal footing. This is all about, for the first few minutes of this lesson, with your eyes and ears and your senses and your noggin, what sense do you make of this? So let me actually put my microbit down for a moment. And because I've got this nice enlarged version of a microbit on the screen, I'm just going to mouse around a microbit here. If you've never seen one before, it's worth just a look around what's on it. So the first thing is this 5x5 grid of red LED lights, and that's used as a readout screen or a display. You can put icons, you can put numbers, letters, scrolling messages. You can plot points on this field of LEDs with an XY grid by coordinate. Another thing that jumps out is these two buttons here, A and B. And when you hold the microbit in your hands, it has this wonderful Nintendo feel to it. It really lends itself to, oh man, I want to play games with this thing. It's very, very interactive, but only two buttons, so it's approachable. It has a strip of connecting pins down here, and these can be used for connecting to third-party electronics kits, STEM kits that you can buy from other providers, or just with alligator clips or aluminum foil, you can connect up to circuitry and attach the microbit to other accessories. On the back, which you can't see there, it's got some sensors built in. I can see the processor. I can see the circuitry. It tells me here that there's an antenna. This can send and receive radio signals between microbits, and it can send and receive Bluetooth messages from your tablet or computer. A reset button here. There's an accelerometer built in, so the microbit can sense when it's being moved or tilted or accelerated. You can use that for science projects. What else? There's a magnetometer on here, which can act as a compass if I calibrate it, and a temperature sensor that's built onto the chip, so it can be a very rudimentary thermometer, and right? So I've powered this one by connecting it to a USB cable to my laptop that I'm doing this presentation on right now. So it's powered. You can see my yellow LED is lit up here. But you can also attach it to a battery pack and then untether yourself from a computer and use your microbit in the field. So microbits are good for gym class, for taking measurements out in a field. in school. So they're a really versatile, accessible tool. You can do a lot with microbits. So I'm going to begin with this notice and wonder routine, and I'm going to pause my sharing for the moment and just concentrate here, okay? So I've got a microbit in front of me, and I want you to notice what it can do. Tapping the A button, it's not doing anything with that. Tapping the B button, it's not doing that. If I invert it or tilt it, that doesn't seem to be doing anything. And as you can see, it's not connected to any circuitry or other accessories. So what is this microbit set to do? Well, one thing I mentioned that I haven't tried yet is to shake it. So if I shake it, something appears on the screen. And I'm going to stick a little piece of masking tape over the front here. This is a trick we've learned in the classroom, that when you have a piece of tape or a Post-it note or something over it, it's just a little easier in full daylight to see those LEDs. So I shook it, and what is that? So those of you that have some experience with microbits will immediately know what that is. Let me shake it again. Oh, that didn't change. Nope. I shook it again. Can you figure out what this is now? This is a canonical introductory microbit project. I've built a rock, paper, scissors game here, right? So it uses the accelerometer that's built in. And the instructions I've given it are, when I shake it, randomly pick rock, paper, or scissors and show it on the LED screen. So this is a great introductory project, but I'll leave this here. And I'll come back to my presentation. So now we're going to start building these projects, okay? A series of 5 projects that I'm calling click counting. That's the kind of project we're going to do. We're not going to get into circuitry or taking data measurements or angles or anything like that, although the microbit can do those. Today we're going to focus on number sense, numeracy. So the overall outline of all 5 projects is the same. We're going to instruct the microbit to remember a numerical value, keep that in its computer memory. When we click the buttons, it's going to do a math operation on it, and then it's going to show the value on the LED screen, and that's it. Super, super simple. Okay. The first one is a simple click counter, and I'm just going to focus on the first one here, and then we'll flip over to the microbit interface, and we'll actually build this. A simple click counter. When I power up the microbit, I want it to start by remembering a value of 0. We're going to use a variable to do that. When I click a button, I want it to add 1 to that value, and then show the value, show the current value of that variable. Okay, and when you've got this built, it's easy to imagine it being used in the classroom to keep score, if you're playing a game in class or in gym, to count off steps if you're measuring something, or even to act out some simple addition problems. So let's move over to my browser. And did I have the URL? Yeah, I'm going to leave the URL here for a sec. If you've never been there, this is the URL to go to: makecode.microbit.org. So much like Scratch, if you've ever used that, or most other block coding platforms these days, all of your coding takes place right in a web browser. You're on their website, and the people who built this have given us a whole vocabulary of instructions that we can use in the form of blocks to give instructions to a microbit. Okay, so down the center here is the entire vocabulary, the entire instruction set that they've given us. And like in other platforms, these are color-coded by theme. So they've decided there are a certain set of core instructions that are the most common to use, and they call this the basic group. Then there's inputs, and that's anything that uses the data sensors or the buttons. There's music, there's LEDs where you can plot and unplot the LEDs on the screen by X, Y coordinates. There's radio communication and mathematical operations. We'll get into those in a moment, and on and on and on. But just to orient you to where you are on the screen, the vocabulary that you have to work with, your instruction set is here in the middle. You're going to actually drag those blocks onto the workspace here where we build the script of what our microbit is actually going to do. And then over on the left, they've given us this nice emulator. That emulator can do basically anything a real physical microbit can do, which is wonderful. It means that when we go into classrooms, if they've got microbits or if they don't, first of all, every kid doesn't need to have their own. We do pairs or triples. So your microbits can go farther than one-to-one, which is nice. But also you can do this on a computer without a physical microbit. And I'm betting that most of you don't have a microbit at home while you're attending this conference remotely either. So you'll be able to do all of this coding and test out everything that you do inside this emulator. Every time I add or change to my code, that emulator is going to refresh. We'll see that in a minute. And then we can run our program and verify that it does what we want to do. So as I showed you in our first routine, this is a click counter. If you can still see in my small window here, I'm going to stop presenting. We'll come back to this for a sec. All this does, my click counter, is it starts at 0 when I start up. If I hit the reset button on the back here, it starts back at 0 and it displays its value. Every time I click, it counts up. That's all it does. Super, super simple. And in fact, we can accomplish this with 4 lines of code. And this will keep going and going and going. And what's going to happen when we get to 10? It just automatically starts to scroll, right? Because it can't fit that number on a single screen full, so it scrolls. So that's it. I'm going to leave that down. Let's come back to make code. Every make code project, when you start a new one, starts with these 2 starter blocks. The microbit is ready to take anything that you want to do when it first powers up. Is there anything you want me to do to get started before your program really gets going? Yes, we're going to hold on to that. And is there anything that you want running forever and ever and ever in the background in a loop while it's doing other things? And in this case, no, I'm not interested in that. So code along with me, or you can wait a few minutes until I'm done. I'll take a pause and you can copy what I've done. The first thing I need to do in my algorithm is create a counter. I need to create a value that the microbit is going to hold in its memory. And I'm just going to call that count. So in the world of math, middle school algebra, you don't tend to use variables that are a word, right? A variable in mathematical sense is usually thought of as a single letter, a Latin or Greek letter. But in the world of computing, we typically give them descriptive names because it's easier to remember what they're doing than if it's a simple letter. So I'm going to create a variable. I did a little 2-step here. I created a variable. I did make a variable. It gave that to me now, and it created a block that wasn't there before. And it gave me these other blocks, which is I can set that variable to have a value of my choice, and I can change that variable incrementally by some value that I want. And these white ovals here, I can fill in any value that I like. So what I've done so far is I set count to 0. And the next thing I need to do, because on my emulator, like, it's done that, but I don't see it because I haven't told the microbit to actually put that out on the screen. So I have to set count and then show, but I don't just want to show the number 0. I mean, I could change that to show the number 1 or show the number 2. And you'll see my emulator is refreshing and it just shows what I'm telling it to show. But that's not a counter, right? That's me coming in and messing with my code, doctoring my code each time. What I really want to do, and this is the first leap that you're going to have to make with your students, is using a variable and plugging it into that oval. See that? So one cool thing about block programming languages that makes it really helpful for beginners is things are not only color coded, but they're shape coded as well. So the shape of that 2 is an oval. That suggests to me that I can snap in this oval block inside it, and that works. So already I've got my first 2 instructions. When it starts up, it's going to set a variable called count to 0, show that number on the LED screen. Okay. But so far on my emulator, I can see the A button isn't doing anything. I need to tell it that it's going to do something. So on my inputs, I have on button A pressed. So I'm going to get a second set of instructions that this microbit knows how to do. And I could say, when button A is pressed, do these instructions, or B, or even A and B together. For now, I'm going to stick with A. When A is pressed, again, I'm going to come back to that variable group. I'm going to change that count by 1. Okay, well, it doesn't seem to be doing anything. And why it doesn't seem to be doing anything is that I haven't shown what that value is now. I keep changing it and changing it and changing it, and I have to trust the microbit's doing that in its memory, but it's not updating that display, so I got to ask it to do that again. Show number, and I dragged it underneath this instruction because things execute step by step from top to bottom. And just like I did up here, I have to show, which number do I want to show? Count is the number I want to show. That's going to be a numeric value. So I think that even may be it. Look at that, 4 lines of code. Does it work now? Voila. And just like my demonstrator, I can keep tapping and it goes up and up and up and up and up. Okay, stop. I've reached a plateau. This is my click counter. It's done. And so in the microbit interface, if I want to save that, I'm going to call it, how about simple click counter. Click that save icon. It downloads something on my browser. You'll notice that it does the same, and downloading is a whole other thing. When we teach microbits in the classroom, you need to know how to download your instructions from the browser to your hard drive or your Google Drive, and how to get that over a USB cable into the memory of your microbit. That we're not going to deal with that right now. That's its own thing. But there are nice tutorials online. For now, I'm just going to stay in the browser. Simple click counter. I have my plateau. I've stopped. And in fact, I'm going to go home. So I'm back on makecode.microbit.org. This is the home page that I was at before. And you'll notice that in my projects, I now have this thing that I just saved 35 seconds ago. So if I ever came back to this browser on this machine, it would keep this and a history of every other project that I built here. Even if I don't download the code file and put it on the microbit, it's held here in my browser. And if I want, I can save that to my machine. I can email it. I can upload it to my classroom app and save it that way, like a file. For now, I'm just keeping it in my browser. And I'm going to flip back to my presentation. So we've done this simple click counter. I'm going to keep moving ahead. I'm now going to do a skip counter. And what does that algorithm look like? Start with 0, just like we did before. When the button is clicked, add something. Well, as a teacher, I can choose strategically, like, what numbers do I want my students to play with? Is it just adding by adding 1? Well, what if we're ready to start adding 2 and adding 3 and adding 5 and higher numbers, and then show the value? Same outline. And once we've got a microbit that works that way, what are the sorts of tasks that we could do? Oops. We could practice addition, skip counting. I could ask you the Marian small way. I could ask my students, okay, how could you get to the number 24 just using 2s with your skip counter? How many skips does it take? And you're prompting them to learn repeated addition. If I wanted to do it a more Marian small way, I would then ask, well, what are the different ways you could get to 24? And you'll see what I mean in a sec. So let's go back into the simple click counter. I'm just going to start here. I'm going to make some changes, and then I'm going to give it a new name and save it, and I'll have 2 projects. So on start, it's going to initialize a new variable, code speak. On button A pressed, it's going to change the count by 1. I'm going to change that to change the count by 2. Now, let me just test that and see if it works the way I think it will. 2, 4, 6, 8, 10. Okay, right away, if you've got that built and you hold that up at the front of the room, you've got a choral counting exercise that you and your students can fiddle with. So that's button A. Let's say I'm going to make button A be skip counting by 2. And I want to give button B something else to do. So I'm going to drag that into my screen here. On button B pressed, did you notice there it came as button A and it was grayed out like that? That's the microbit interface telling us we've got 2 things that are trying to work on button A, and it's not going to allow that, so it disables one of them. But if I switch this to B, then they'll both work. I want to just kind of copy that code, change the count by 5, let's say. And again, show a number. Which number do I want to show? I want to show my variable, count. Okay, so my emulator just refreshed. It came back. Let's see. I have a skip counter with 2 on the A button. And if I click B, it skips from 6 to 11. And now to 16. And now to 21. Great. And I'm going to call this one, instead of simple click counter, I'm going to give it another save. And I'm going to call it skip counter. Okay, and when I go back home, I now have skip counter. And I can come back to that. Oh, did I not save that properly? Whoops. Save skip counter. Okay. And it downloads this thing that's a hex file, right? Like a PDF or a doc or an XLS. This is a hex file. And that's the code file for any microbit project. So let's come back to the presentation here. We've done the simple click counter. We've done the skip counter. In fact, I told you I would pause and leave my code on the screen for you to copy, and I forgot that the first time through, so let me pause here. If you're watching the recorded version of this, of course, you can pause, and then I'll continue momentarily. Okay, so let's continue with the third project. Now, we have button A and B doing different skip counts. What if we did button A adds 1 and button B doubles my variable? Well, if that's your algorithm, then in your routines you get richer. You can start practicing doubling. Instead of just addition, you're moving into multiplication. And I can ask questions in the Marian small vein like, students, how can you get to 25 by adding 1 and doubling? What are the different ways that you could get to 25? Or pick a number strategically based on your pedagogical goal. What are you trying to get your students to get right now? So it's just a hop, skip, and a jump from the skip counting to add and double. I'm going to take button A and turn that to changing the count by 1. Refresh my emulator. Is that still working? 1, 2, 3. Okay, skipping by 1 or adding by 1. Great. And then on button B, I want it to double my variable. So here's a programming trick. I could do this a few different ways, which is often the case in programming, just as in math. I could think of it as adding count to count. I could think of it as multiplying count by 2. And I've got all the basic and advanced mathematical operators here. But the simplest way to think of it, rather than multiplying, is just adding. So I'm going to change count by count. How's that for meta? I'm going to change count by count. So that's a very programmy way of thinking of it, as opposed to a math way, which might stretch your students' thinking. So maybe they'll just want to copy this. But if you've got change count by 1 and change count by count, effectively add 1 and double, then here's what I can do. I can add 1, add 1, add 1, and then double. How about that? And then I reset it. It goes back to 0 because it runs this code. Add, 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 double, double. Nice. So I'm going to come back to the presentation here, and I want to share a transcript. So I did this with one of my kids at home. And I recorded it because it was such a great example of what you might expect to see in the classroom. So my son is in grade 4. He's 10 years old. So he's been multiplying now for a year. Like this is not new to him, but it pushed his thinking a little bit. He had to slow himself down and make sure he was reasoning correctly. So I think this is the kind of thing that you can do in a math classroom with older kids as well, to push their thinking and get them to slow down and be deliberate. I said to him, okay, if this were my microbit, how could you get to 12 starting at 0? And his first answer was, well, I would count up to 6. Here, I have my microbit, so I'll do this in the window here. I could count up to 6, and he said count, not add 1. He said count, which pedagogically is interesting. And then double it, double, and it jumps from 6 to 12, and I've reached that. I said, okay, well, can you give me another way? And his response was, well, okay, count to 3 and quadruple it. And I strategically didn't want to just say, okay, great, quadruple it. I asked him, I pressed a little. I said, well, what do you mean by quadruple? And he said, oh, okay, get to 3 and then double it 2 times. So I'm forcing him to slow down, not jump ahead, and justify how he's going to get there. I said, okay, another way. And he said, well, this time, okay, count up to 4, double it, that's 8, double it again, and he caught himself. Oh, wait, if I double it at 8, I'm going to get 16, I'm going to go over. It's like watching him think through a hand of blackjack. I said, right. So, okay, stop at 8 and just count the rest of the way, 4 more, and that reaches 12. And then I changed it up. I said, well, what about getting to 11? And he said, okay, well, then I would count to 4, I would double it to 8, and then count the rest of the way. And what I want to highlight here is he's showing counting on, he's showing repeated addition, he's showing multiplication. All of these things that in an instructional routine, you know these are goals that you're trying to get to. And my hope is that this microbit project will help you get there. Okay, final 2 projects. I'm going to buzz through these. A single place value digit. So when you're teaching place value, stop sharing and just go in my window here. When you're teaching place value, oops, you don't want a counter that's simply going to go up to 9 and then 10. Students need to understand that place value means that a single digit is counting how many of my unit. If I'm in the ones position, I'm counting how many ones. And 11 ones really is a 1. And which way am I focusing here? A 10. So you want it to do something different than counting up to 11 or counting up to 10. When you're teaching place value, you want them to understand a digit that cycles from 0 to 9 and then recycles again to 0. So we can model that in a microbit. And I'll share again. So what does that look like in a microbit? Well, I'm going to get rid of button B. I'm going to say when button A is pressed, I'm going to change my count by 1. And I want to just be able to repeat, right? But I have to build in a logic check. If I reach 10, then what I actually want to do is reset myself back to 0. So what does that look like? I have to come into the logic. If true, then this, and I'm going to squeeze that in the middle here. Change the count by 1. If I just reached 10 by adding 1 more, and that helped me reach 10, then really what I want to do is reset back to 0. So I've introduced a new shape here. When you're dealing with logic, testing whether things are greater than, less than, true or false, this uses a hexagon shape. And those are all this green, and they're in the logic section. So I have this check if one number equals another number. And I can also do doesn't equal, greater than, greater equal to, less than equal to. If count is equal to 10, then what do I want to do? I already know how to do this. I'm going to set the count back to 0, right? Same instruction as I have here on start. Change the count by 1. If the count just became 10, then set it back down to 0. If that's not the case, if I'm still at 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, then I don't do this. I continue down my logic, continue down my sequence, and then I just show the number count. So reload this. 1, 2, 3, 4, 5, 6, 7, 8, 9. What's going to happen next? 0, not 10. It didn't scroll. It's just 0. Now, is there any way for me to test what that count is right now? No, I can just output it to the LEDs. So I think this is working now. And I'm going to call this single digit. How about that? It's going to give me my downloaded hex file again. I'll X that away. Okay. So what's the last one I wanted to do? I could say that you can extend this to other instructional routines, other tasks. What if you had 3 students doing 3 microbits, and each of them had to build a single digit that rotated from 0 to 9, and you asked them to act out 2-digit or 3-digit addition using place value? The first student in the ones position would go up a certain number of units, and then you'd force them to carry the 1 somehow. How are you going to carry the 1? Well, you could elbow your neighbor here and say, you go up 1 digit, and they'd have to do that too. So this is something I tried with middle school students who've been doing addition, for 5 years, but it forced them to understand what does place value really mean. And so mathematically, that's not a big stretch for them, but it is a coding stretch for them. So you see the balance start to shift between pushing the mathematical thinking and pushing the coding thinking. And in fact, this last one that we're going to do, counting with multiples, is sometimes used as an exercise for introductory computing, even at the high school and university level. So you may know this. Let me just check that I'm sharing. Yeah. You may know this game as fizz buzz, or you may know it by a different name. And the idea is it's almost like a choral counting game. As a class, we're going to count, or maybe we're going to count 1 student at a time, just counting up by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, et cetera, et cetera. But every time I reach a number that's divisible by 3, every time I reach a multiple of 3, instead of the number, I'm gonna give a special signal to show that I know I'm divisible by 3. I'm going to count 1, 2, and the special signal is usually fizz. So choral counting like this may be confusing. Choral counting like this around the class would sound like 1, 2, fizz, 4, 5, fizz, 7, 8, fizz. And that on its own is a good choral counting exercise. Where it really starts to get tricky is if you press it a little further. And the classic version I know is 3s and 5s. So I'm watching out for multiples of 3, and I'm watching out for multiples of 5. And 5 gets its own separate signal. So 3 is fizz, 5 is buzz. Choral counting like that would look like 1, 2, fizz, 4, buzz. And then 6, we're right back to fizz, 7, 8, buzz, fizz, and so on. This sounds like it's easy, but man, it's hard to focus and get it right, and the class will probably be in giggles before too long. So like I say, this is a real programming exercise. This is where we reach the point where the coding is more difficult to do than the mathematics. The mathematics here is you're just listening for multiples, right? But the coding gets a little trickier. So I'm going to go ahead and code this. And I'm using this single digit place value as my starting point because it has this nice little if in here. What I'm going to do is I need a remainder because that's actually the mathematical operation I need to do. Every time I change my count by 1, I need to check whether the remainder of count divided by 3 is 0. That's how I'm going to check in coding terms with the logic and the mathematics that they give me here. That's how I can express a check for, is this number count now divisible by 3? I have to say in a roundabout sort of way, is the remainder of count divided by 3 0? If so, then I'm going to show, in fact, what I'm going to do is show, no, I'm not going to show LADs. I'm going to show a string. Get rid of that guy. If the remainder of divided by 3 is 0, meaning this is divisible by 3, then I'm going to show the string f for fizz, a text string. So in programming speak, that's what we mean by text. I've got this plus here. I'm going to expand that, and now I have a second condition. Suppose it's not divisible by 3. Suppose this logic check is not true. What else might I do? Else, I'm going to show the number count. So let me stop there and try this in the emulator. 1, 2, fizz. 4, 5, fizz. Okay, see? That's not bad. Okay. If I want to add buzz, well, then I need to add another if-else condition in here. And I'll show you a shortcut at this point. I can right-click in this environment on any code block, and I can duplicate it. And that's a nice shortcut. Oops. That's a nice shortcut for having to reconstruct that whole thing. If the number count is divisible by 3, I'm going to say f. If it's divisible by 5, I'm going to show the string b for buzz. Else, I'm just going to show the number itself. Let's try that. Reload my emulator. 1, 2, fizz. 4, buzz. Fizz. 7, 8, fizz. Okay, great, it works. Got lucky. And now the crowning achievement of every fizz buzz game is what happens if it's divisible by 3 and by 5. So mathematically, what does that mean? It means it's divisible by 15, right? I'm going to have to do that check. I know as a programmer, because I've done this before, I'm going to have to do that check at the top of my list because that supersedes everything else, which forces me to do some some messing around here. And in fact, I'm going to take a shortcut. I'm just going to load my FizzBuzz game right into my emulator. And you'll see my finished product. Let me zoom out just a little bit here. Same as I had before, when I start up, I set count to 0 and I show it on the screen. When button A is pressed, I change the count by 1. Then I do my logic check. If count is divisible by 15 evenly, then show these LEDs on the screen. And it's kind of a crude FB. If it's not divisible by 15, then I go to my next check, which is it divisible by 3? If so, then fizz. Is it by 5? Then buzz. Else, if it's not any of those, then I get to just show the number. And then what that looks like is this: fizz, buzz, fizz, fizz, buzz, 11, fizz, 13, 14, and did I get it right? 15, fizz, buzz. Okay, so I'm going to leave fizz, buzz here on the screen for just a moment. And we'll now head back to the presentation. So if you have FizzBuzz built, you don't have to play FizzBuzz with it. Really what you're focusing on is multiples and skip counting. So you can ask questions like, okay, class, how can you get to 24 with just 2s? Build a microbit that does that. And how many 2s does it take? What are the different ways we can get to 24? If I let you do skip counting in different ways. Did I do that before? Yeah, okay. So I've done all my demonstrating. We've done 5 projects. What I hoped to achieve in this session was to help you build your own manipulatives that you can use in your instructional routines. You're at OAME, so I can assume with some confidence that you're an experienced math teacher. You've got instructional routines. You know how you like to teach number sense. And my hope is that projects like these with a microbit will fit right into your routine and be something that you think will help when you incorporate it into class. And hearkening back to Graham Fletcher at last year's OAME, the model is, let's build a working computer program. Let's solve a problem in order to learn math, right? The mathematical thinking really begins once this is built. There's some amount of thinking that goes into this, especially FizzBuzz, that gets a little complex. But those click counting ones are so simple. They could just follow you in building those, and really the thinking starts once they've got their manipulative. And we went through these 5 projects: the click counter, skip counting, add and double, the place value digit, and then finally FizzBuzz. Overall, my goal is to make it clear that these support 2 strands very clearly in the Ontario curriculum: number sense and numeration, and patterning and algebra. And those can be applied, of course, at different levels of sophistication with different students. Of course, microbits can do a lot more. You can plot on the LEDs, as I said. You can measure angles, work on messaging between microbits. There's all kinds of things you can get into. So I encourage you, if you're interested in microbits, they're not expensive. A box of 10, a classroom set, something like $250. So compared to a lot of other kits that you can buy, this is pretty cost effective. And there's a lot you can do. They're friendly and accessible. So thank you very much again to the OAME organizers and to you for watching my session. If you'd like to learn more about Kids Code Jeunesse, bring us into your classroom or bring us in to do professional development with your school, your board, or your region, contact us at our website, kidscodejeunesse.org. You'll also see us on social media as Kids Code Jeunesse or Kids Coding. And of course, we also have Code Club Canada. You can search for us that way. Thank you very much. And enjoy the rest of the conference.